So now that we know what factors affect the reaction rate, how do we actually go about calculating it? Well, rates of reaction we usually measure in units of concentration per time, because if you talk about how quickly a reaction is happening as a reaction goes on, is that the concentration of your reactants will decrease. So if you started off by having, let's say, a decomposition reaction, let's just do a little net ionic sort right here, where NaCl will decompose into a sodium ion plus a chlorine ion as it dissolves, is that we originally would start off with a lot of NaCl, and then over time that NaCl would decrease, and so its concentration would drop. And so usually we'll give it in units of concentration per time. This unit we still use, even though it really doesn't make a whole lot of sense if you're talking about solids. It would make more sense if you're talking about liquids or gases or aqueous solutions. We're still going to use it anyway. But it's concentration per time, and we're going to give this typically in molar concentration per second, moles per second, molar per second. So that's basically the unit we're going to use. Now, let's suppose that we did have some reactant. We'll call it A. Let's just say for right now that we're going to have a really simple reaction where A reacts and turns into X right here. And so the reaction rate of reactant A, we're going to give by this little equation right here. That the whole reaction rate's actually the whole thing. I left out that part. Whoops. So this is our equation right here. So the reaction rate of reactant A in that little equation where we said A reacts to form X is going to be the negative of the change. Remember that little delta sign means change, little triangle means change. The change in the concentration of A. Because remember we said those brackets back in equilibrium mean basically concentration of. So the change in concentration of A divided by the change in time, take the negative of that, and that's the reaction rate. So let's go in a little more detail on this just to make it clear what we mean by this. So number one, when we say something like change in concentration of A, remember anytime you have a change in something with that delta, what that really means is that it's the final concentration minus the original concentration. That's sort of the form that means. So if we said change in concentration of A, that's going to be equal to the final concentration. So the final concentration usually we're going to give like this, just an A in a bracket, minus the original concentration. Usually the way we'll write the original concentration is we do it exactly the same, but we put a 0 on the outside like that to show that it's the original concentration. So if we know that a substance were to start at a concentration of 5 molar and end at a concentration of 3 molar, then what we would do is we would say that the final concentration is 3 molar, put that up here. The original concentration was 5 molar, put that up here. And so in this case, our change in concentration, delta A, would end up being -2. And so -2 molar would be our change in concentration there. But we have this other part in here. We have to divide it by the change in time. And usually I'll just write this as time, but it's basically the time it's taken to go between this starting and this ending concentration. How long did the reaction take to go from your original concentration to your final concentration? Now, you do want to notice here this is negative, and the reason why is because this came out as negative, right? Whenever you have a reactant, reactants get reacted, their concentration drops, and we're going to have as a general rule reaction rates must be positive. So for reactants we have to put a negative sign out front, but for products we do the exact same thing. The only difference is for products is there's no negative sign because the change in the concentration is always positive. If we were doing our X right here, it would maybe even if this were the exact reaction, A turns into X right here, then we would probably end up finding that for X, the original concentration of X might be something like 0 because there wasn't any to start with, and then the final concentration of X might end up being 2 molar. That's a 2 right there. My 2's not showing up. 2 molar right there, and so then we would end up going ahead and figuring out, okay, well the change in concentration of X is just going to be the final 2 minus the original 0, and so it just ends up being 2 molar. It's positive. And then we divide that by the time to figure out what the reaction rate was of X. And so typically when we're doing this for an individual thing, we the way we'd say it is we'd say the reaction rate of reactant A, or the reaction rate of product X, or you could just say it the reaction rate of A or the reaction rate of X. Either one works in terms of setting this up. Now, let's look at an example how you might do this. Suppose that we started a reaction in a 2-liter container with 4 moles of N2. So N2 is going to be our reactant, okay? And into the reaction 12 seconds later with 1 mole of N2. What's the reaction rate? So it really doesn't tell us if we're reacting N2 with anything or what it's going to turn out as. Doesn't really make a difference in terms of solving this. All we know is that we're trying to find the reaction rate of N, okay? And so we want to figure out what is the rate of N2, of nitrogen gas. Now, what we know for this is that since N is going to be a reactant, the general form for the rate here is going to be the negative of the change in concentration of N2 over the time, right? Just like that. So what we're going to have to figure out is what is this change in concentration of N2? Well, to figure that out, we're going to figure out what is the original and final concentrations. So let's look at the original concentration of N2. Well, this concentration is in molarity. And if you remember, molarity is always going to be in moles of solute divided by liters of solution, if that'll fit on here. Okay, so moles of solute over liters of solution. And so in this case, nitrogen, N2, is going to be our solute. So how many moles do we start with? Well, it says we started a reaction in a 2-liter container with 4 moles of N2. So we're going to say 4 moles on top divided by the liter solution. That's the volume since it's a gas, and it tells us it's a 2-liter container. So 4 moles divided by 2 liters. And so the concentration, the original concentration of N2, is just going to be 4 divided by 2, so it's just going to be 2 molar. All right, so that's our original concentration. Our final concentration of N2 is going to be same thing. Number of moles, which afterwards is 1 mole, divided by the number of liters, which is 2 liters. So that's just going to end up equaling 0.5 molar. All right, so once we know that, we can go ahead and figure out this rate, because the reaction rate of N2 is going to be equal to the negative of the change in the reaction in the concentration. And so remember that change in concentration is always the final minus the original, and our final was 0.5, our original was 2 molar. So we'll say 0.5 minus 2 molar divided by the time. And how long does it say this reaction takes? The reaction said we started the reaction, 4 moles into the reaction 12 seconds later. So we'll say divided by 12 seconds. Okay, so 0.5 minus 2 is negative 1.5. A negative of negative 1.5 is positive 1.5 divided by the time. It's molar, 12 seconds. And so we do that. The rate, the reaction rate of N2 should be whatever 1.5 divided by 12 is. It comes out to be 0.125. 0.125, and our unit here is going to be molar per second. Now, sig fig wise, everything here except for the 12 has all got 1 sig fig. We're really doing pretty much all multiplication, division, a little bit of subtraction here, but it's going to be in 1 sig fig. So our final answer here would be just 0.1 molar per second is going to be the reaction rate of the nitrogen gas. Let's try another one. Combustion reaction of methane in a 16-liter container produces 0.48 moles of carbon dioxide in 8 seconds. What's the reaction rate of the carbon dioxide? So this is methane. It's being reacted, produces 0.48 moles of carbon dioxide in 8 seconds, the reaction rate of the carbon dioxide. So we're looking for the reaction rate of carbon dioxide. So we're looking for the rate of CO2. Now, because the fact that it's producing the carbon dioxide, that means this is a product, and the product, the form is always, we don't have the negative sign, right? So it's just the change in concentration of CO2 divided by the time should give us our rate of that. Now, for that CO2, we're going to still have to figure out what is the original and final concentrations of those. So let's try that out. So for our CO2, original concentration of that, let's see. It says combustion reaction of methane produces this many moles of carbon dioxide in 8 seconds. Well, it didn't specific on here, but I think we can probably imply that if it just started off with methane, and obviously it's going to have oxygen if it's combustion, there wasn't any carbon dioxide to start with. And so if that's true, the number of moles of carbon dioxide is 0 moles. And in the 16-liter container, which obviously is just going to be 0. So there's 0 molarity is the original concentration of the CO2. All right, so then we have to look at the final concentration of the CO2. Final concentration of CO2 is going to be the number of moles, which ends up being 0.48 at the end, divided by the volume, which is 16 liters. Okay, and so whenever we calculate that, the final concentration of the CO2 is going to end up being, let's see, divide that out, 0.03 molar. Okay, and so to find our change, change in the concentration of the CO2 is going to be the final minus the original. The final was 0.03, the original was 0, so it's just going to be 0.03. So that means the rate of our CO2 is going to be equal to 0.03 molar divided by the time, and the time here is 8 seconds. It tells us for the reaction to happen, so divided by 8 seconds, and so that means our reaction rate of the CO2 should be equal to, just divide those out, I get 3.75 times 10 to the negative third on units of molar per second. Sig fig wise, we have 2 sig figs, 1 sig fig, 2 sig figs. That 8 seconds is going to mean that the final answer has to just have 1. So its final one just ended up being 4 times 10 to the negative third molar per second is our final reaction rate of the carbon dioxide. So let's take a look at another reaction here. So in this particular fellow, we have hydrogen gas and oxygen gas being reacted to form water. And let's just make this a really easy reaction rate problem. Suppose that this takes place in a 1-liter container. Okay, this starts with no water. It ends with 1 mole of water. Okay, and takes 1 second. So all ones here just to keep things nice and simple. Now, if we think about this, we know that the reaction rate for the water, since it's a product, is going to be the change in reaction of the H2O over the time. Well, but the change in reaction of H2O, it's in a 1-liter container and it starts with none. So the original concentration is 0. So the original concentration is 0. And so it's final minus original. The final concentration of the water, it's 1 mole over 1 liter, so it's just 1, then divided by 1. So that means that our reaction rate for the water is just going to be 1 molar per second, because it just changes of 1 mole in 1 second in 1 liter. The number of moles is going to be the same as the concentration because it's in a 1-liter container. So that means that our rate of H2O is just going to be 1 molar per second. But let's take a look at the other ones here. Well, mole ratio wise, there are 2 H2Os here and 2 H2s. And so that means if this produces 1 mole of H2O, it must have used 1 mole of hydrogen gas because the mole ratios are the same. If you wanted to prove it, you could see it by doing a mole conversion where you said just 1 mole of H2O, and we'd say the mole ratio moles H2O over in moles H2, and it's going to be a 2-to-2 ratio, and so it just equals 1 because the 2's just cancel out, right? It's going to be just a mole ratio here. But if that's true, that we started off with 1 mole of H2, we ended with no H2 because it reacted all of it. The change in concentration is going to be -1, and since it's a reactant, it'll be negative of -1, and that means that the rate of H2 is also going to be 1 molar per second because all the numbers are the same for it. But what about the O2? Well, the O2 doesn't have a 1 in front of it. It's got a mole ratio of 2 to 1. it's going to produce not 1 mole. It's not going to be. We're not going to use up 1 mole of oxygen. We're only going to use half a mole because that's what the mole ratio says. Which means the change in concentration is only going to be half a molar. Which means that the rate is just going to be 0.5 molar per second. Take a look at these rates. 1 to 0.5 to 1. Look at the coefficients. 2 to 1 to 2. 2 to 1 to 2, and 1 to 0.5 to 1. But if you take those, the 1 and the 0.5 and the 1, and you multiply them all by 2, guess what you get? 2 to 1 to 2. Turns out that if you have a balanced chemical equation, if you know how to balance it out, you can find the relationship between the reaction rates of each of the reactions, of each of the substances. They're just related by the mole ratio. And so, this ends up being a really good way that we can manage to convert from one to another. But even more than that, this lets us be able to figure out what we're going to call the overall reaction rate. That is, based on what the reaction rate is, not in terms of H2 or O2 or H2O, but in terms of moles reaction. And so, this ends up being sort of quite helpful. So, let's suppose that we have some chemical reaction that's this form, where lowercase a and lowercase b and lowercase x and lowercase y are the coefficients. A, b, x, and y are a and b are the products, the reactants, and x and y are the products. And so, if we did that, the overall reaction rate of the whole reaction is basically going to be 1. For at least the two reactants, that's these two guys right here, negative 1 over the coefficients, see A and A, times basically the reaction rate, which is what we got before, the change in the concentration of A over change in time, and then for B, 1 over B, the change in the concentration over time. Now for X and Y, no negatives because they're products instead of reactants, but it works the same way. 1 over the coefficient that goes down right there. There's a coefficient right there in the concentration here. We can work out and figure out what the overall reaction rate is. So it looks more complex than it is. Let's work one out and see how this would turn out here. So I got our equation along the bottom. 2 moles of nitrogen gas are reacted with excess hydrogen in a 10-liter vessel. If the reaction takes 80 seconds, what's the average reaction rate? So when it says average reaction rate now, it doesn't say the reaction rate of the nitrogen, doesn't say the reaction rate of the hydrogen, just the overall reaction rate. And that's what we're going to be looking for here. So in order for this to work, we have to balance the equation. So it tells us we have nitrogen gas, N2, reacted with excess hydrogen. Hydrogen, because it's GEN, is H2. And then let's see what it's going to form here. Well, you may recognize this is forming ammonia, because nitrogen, which is going to be a -3, hydrogen is a +1. So we end up with 3 hydrogens and 1 nitrogen, which we usually write like this, NH3, ammonia. Now we got to balance it. And so to do the balancing on here, we have 2 nitrogens and 1 nitrogen, so we put a 2 out there. That gives us 2 times 3 is 6 hydrogens, so we've got to put 3 out here like this. All right, so that's going to give us our balanced reaction here. So once we've done that, we're looking for the average reaction rate. And so we're looking for this reaction rate down here. It tells us there are 2 moles of nitrogen react with excess hydrogen. It takes 80 seconds. Now, 2 moles of nitrogen gas are reacted, and the reaction's over in 80 seconds. The hydrogen's excess, which means nitrogen is the limiting reagent, which means the nitrogen gets completely used up. So if the nitrogen gets completely used up, then we can sort of say, all right, let's figure out our concentration. So the original concentration of the nitrogen is going to be simply the number of moles, which is 2 moles. That should be moles divided by the volume, 10 liters. And so the original concentration of the nitrogen just turns out to be 0.2 molar. Final concentration of the nitrogen, well, we can just sort of say that right off the bat. We know that because it's all gone when we're done, it's just going to be 0 molar. All right, so since nitrogen is a reactant, we're going to use this little guy, right down here to work that out. And so this ends up being that the rate of the reaction should be negative of 1 over the coefficient. So let's look at the coefficient of nitrogen. Well, that's just 1. So 1 over 1 times the change in the concentration. So it's always final minus original. The final was 0 minus the original was 0.2 divided by the time. Time here was how many seconds? 80 seconds. So negative 1 over 1 times 0 times 0.2, we can go ahead and work that out. So this of course is just 1 right there. That's not 11, that's a 1. So we just have negative 0.2, the negative of that because of that negative sign right there, divided by 80. And so when you do that and work that out, I end up getting 2.5 times 10 to the negative third units of still molar per second. Sig fig wise, the 2 is infinite sig figs, 10 liter is 1 sig fig, 80 is 1 sig fig, so there's going to be 1 sig fig. So it ends up being just 3 times 10 to the negative third molar per second is my overall reaction rate. All right, so now we're not just doing the reaction rate of an individual thing, we're doing the overall reaction rate that's going to apply for the whole reaction. All right, so next one that we've got here. Over 40 seconds, the average reaction rate is 0.5 moles reaction per liter per second. And just FYI, if you look at that moles reaction per liter per second, you do sometimes see this written as a reaction rate, but this is moles, moles reaction per liter per second. Moles per liter is just molarity, so this is the same thing as basically saying molar per second. It's just a different way of writing it out. So 0.5 moles reaction per liter per second, or 0.5 molar per second, for the decomposition of carbonic acid in a 2-liter container. If there's initially only carbonic acid, how many moles of CO2 are produced in this 40 seconds? So it tells us that this is decomposition of carbonic acid. Carbonic acid, H2CO3, right there, because it's ic acid, so it'll be carbonate. There's no hydro. Decomposition reaction of an acid. It's a binary decomposition. Acids always decompose into water and the metal oxide. So water, H2O. The metal here is, non-metal oxide, water and the non-metal oxide, is carbon. That'll end up being CO2 based on the valence it has here. To balance those out, two hydrogens on both sides, 1 carbon on both sides, 3 oxygens, and 1 plus 2 is 3. So that actually balances out. No coefficients needed, or the coefficients are all 1s, so we can leave that like it is. All right, so here we are trying to find the moles of CO2. Oh, that's a little different question than we've had before, because we know the reaction rate to start with. So we already know this reaction rate. We're looking for CO2. CO2 is one of the products. So let's use this section right here because we're looking for a product. So we know that the reaction rate, which we already said is 0.05 molar per second, is going to be equal to 1 over x. X is the coefficient. Well, the coefficient out in front here is just 1. Okay, times the change in concentration. So the change in concentration of the CO2, which we don't know right now, divided by the time. It tells us the time it takes is 40 seconds. So 40 seconds right there. All right. So once we have that, we can go ahead and start doing a little bit of math here. So the 1 and the 1 just cancel out right there. That's sort of gone. So we'll multiply both sides by 40. So both sides by 40 to cancel the 40 off the bottom. Right there, 40 times 0.05 ends up, that's 2. So that ends up giving 2 molar, because that's 40 seconds, and the seconds cancel the seconds right there. 2 molar is going to equal to the change in concentration of the CO2. Now, we also know that that change in concentration is going to be the final concentration of the CO2 minus the original concentration of the CO2. All right, well, it says that there was initially only carbonic acid, which means there was no carbon dioxide to start with. So that's just going to go to 0. No concentration here. So that means that the concentration of the CO2 at the end is 2 molar. So, molarity is moles of solute over liters of solution. So the 2 molar is going to be the number of moles of CO2, which we don't know. That's what we're trying to find. So x moles CO2 over the volume, which is going to be, in this case, what does it say the volume is? 2-liter container. So over 2. So multiply the 2 times both sides. That turns out to be 4. So that means we get 4 moles of CO2 are going to be produced at the end right there. And so after that 40 seconds, we should have 4 moles of CO2. And so that's basically sort of how we go about that. If the time had been greater, we could figure out the greater amount. Time had been less, we'd figure out the less amount. So really what this lets us do is it lets us determine, how much of a substance has been produced after a certain amount of time in a reaction. Now, there's one thing that we do have to look at, though. These reaction rates that we've been talking about are average reaction rates. They assume that the reaction rate stays constant over time. And in truth, that doesn't normally happen. We can use it in some cases as a reasonable approximation, but what tends to happen is this. Let's take a look at this graph that's over here on the left, is that on the y-axis, we basically have concentration of our reactant. On our x-axis, we have time going along here. Let's suppose that we started off with this C4H9Cl as our original reactant. We started off at a concentration of 0.1 molar. Now, as this reacts, we know the concentration of the reactant is going to drop. But we also know that reaction rate is dependent on concentration. Higher concentrations means higher reaction rates. Lower concentrations mean lower reaction rates. So the reaction rate will actually change for most reactions as the reaction goes on. And so, whereas what we've been doing is we basically said, hey, it starts here and it ends here. And so to find the reaction rate, we're basically going to take like a straight line type of thing. In reality, what happens is the reaction rate starts high. In this case, it's got a slope that's pretty steep right here. But as time goes on, that slope gets less steep and less steep and less steep. And so those reaction rates, the slope of this line, the reaction rate at each individual point in time, at this point right here, or the reaction rate at this point right here, is called the instantaneous reaction rate. And so it's basically that reaction rate at a particular moment in time. And so the smaller your change in time is, the closer the average reaction rate is to the instantaneous reaction rate. Because remember, this is always, in the form of, it's like the change in concentration over time, that change in time here. And as that change in time gets smaller and smaller and smaller, if you measure it over very, very small times, that average reaction rate and the instantaneous reaction rate get very, very close to each other. And so if you ever take calculus, this is a huge part of calculus that comes in here. We're not going to worry about the calculus part. I'll do all that in the background for you. But that's basically our difference here, is that we have been looking at these average reaction rates, but instantaneous reaction rates are what we're going to look at sort of moving forward here, because that's the one that's going to tell us that, hey, at 400 seconds after we started, what's the reaction rate at that point? But if we go to 800 seconds, that reaction rate is going to be a smaller reaction rate than what it was before, because the concentrations dropped and therefore the reaction rates dropped. And so we'll look at that in a future lesson.